Did she say yes? Oh, not the yes. Yeah. Got it.
All right. So yeah, let me just get some of these things out of the way here. So today we're just gonna practice on problems that we've done. So we'll do a Pythagorean theorem problem. We'll do volume of cones. We'll do problems where we got to involve volume and surface area. And we're just going to practice through the concepts that we learned so far. You may have seen that shadow problem in your homework. I'm going to go over that in detail tomorrow. But today we're just going to try to get more comfortable with what we covered from the past 2 days. So in your packet, page 5 and 6, there's problems 1 through 4. And that's just more review for the concepts that we've learned up to this point. So that's going to be your homework tonight, page 5 and 6. The guide 1 through 4. I will send out a reminder this afternoon, since it's not in your calendar. And I will also send you guys a link to the key so that you guys, as you guys are working through, you can kind of check your answers along the way. Tomorrow and Friday, I will hold help sessions just over, some homework problems that you may have done, that you may have questions about. I'm not going to cover anything new with the help sessions. I just want to, if anybody wants to come in and ask questions about specific problems that we've done or specific concepts, and we'll just get additional practice. Feel free to come in. I will, it'll be in the classroom, but you can also join online, and I will send you guys a Teams link both mornings so that you can click on that link and it'll take you to the Teams page where I'm going to be holding the help session. I will record them as well, so if you miss it, you can always watch it online later. All right, so let's go to page 3. And we're going to pick up where we left off. We did number 1. Now I want us to look at number 2. Okay, so page 3, number 2. Says the volume of a cube is decreasing at a rate of 10 cubic meters per hour. How fast is the total surface area decreasing when the surface area is 54 square meters? All right, so let's build our formulas here. We're talking about volume and surface area of a cube. What do you know about a cube?
6-sided. Each side is x squared. I mean, it's got 6 sides, with each side having surface area of x squared.
Okay, but the volume
X cubed.
x cubed, because the length, width, and height are all the same, right? So volume is 3-dimensional, length times width times height. The length, width, and height are all the same. So if I have x, if I call x being the length of one side, x times x will be my volume for my cube. Okay, and surface area formula, like Sean said, we have 6 sides, and each side has an area of x squared. Remember, surface area, all you're doing here, you're just adding up the area of your 6 surfaces, right? You have 6 surfaces in a cube. Each surface has an area of x squared. If I add all those 6 together, I get 6x squared. Okay, so these are our starting formulas. Let's go ahead and find the derivative. Let's just get the calculus power rule out of the way. And that way we can see all the variables in play for this problem. All right, so V becomes dV. Okay, x cubed becomes 3x squared, right? Finish off your power rule and then dx dt, good. All right, S becomes ds over dt. And then 6x squared becomes 12x, right? We finished doing the power rule for that variable, and then we want to include the dx dt. So Let me just talk about each of these variables here. V is the volume, S is surface area, dV/dt is the rate at which the volume is changing at a specific moment in time. dx/dt is the rate at which the length of the side of the cube is changing at any moment in time. And ds/dt is the rate of change of your surface area at any moment in time. Okay, so let's read the problem here and see if we can assign values to variables here. The volume of a cube is decreasing at a rate of 10 cubic meters per hour. What could that be referring to?
dV over dt,
D-
negative 10 meters.
Good, dV over dt. So a couple of things that are kind of helping us, context clues to kind of give us an idea of what we're dealing with. We see the word volume, but also it's not a static value, right? We see the word decreasing, we see the word rate. There's time involved, so the only thing that we have left is dV over dt. Another thing to kind of help us out is that cubic meters per hour. Cubic meters, that's in terms of volume, three-dimensional units. Per hour, that's time. So cubic meters per hour, that's dV over dt. And then finally, decreasing. The fact that it's decreasing, we know that the volume is getting smaller over time. We want that rate to be a negative. So dV dt. Okay, how fast is the total surface area decreasing? How fast is the surface area decreasing? What is that referring to? ds/dt, right? We know S is surface area, but then we see the word fast. We see the word decreasing. We know it's a rate. So ds/dt is what we're looking for. When the surface area is 54 square meters. That's just what? So that's just S, right? So S is 54. Okay, so let's go to the end of the problem here, right? At the end, we're trying to find ds/dt, and I have a formula for ds/dt. That's great. And if I can just find x and dx/dt, then I can just enter this in the calculator and find that value. But do they give us x or dx/dt? Okay, so they don't give it to us, but they do give us a way to move towards what we're looking for. They do give us dv/dt and they do give us s. Okay. But we need x and dx/dt, so we may need to do a couple of steps before we can get to what we're trying to look for. How can s help us out? From the s, we can insert into the surface area formula, and we can find the what? Find the x. If we find the x, that's one piece of the puzzle that we need for ultimately what we're looking for with ds/dt. So we'll do that first. But then after we find x, then let's say we have the value for x, and we can insert those here. How can the dv/dt help us out?
We can now solve the dx over dt.
All right, we have a dv/dt formula. Insert negative 10 here. Insert whatever x we found. And then once we have dx/dt, then we have the final missing piece, the two missing variables, that values that we can insert and find ds/dt. Okay, so start there. See if you're able to find, using s, find x. And then from x, see if we can find the other missing variable. Okay, I'll go through each step. We saw a similar process with this, with surface area of a sphere and volume of a sphere. So just want you guys to get a chance to kind of practice these steps and see if it makes sense to you. Okay, by the way, if you get done with 2, we're going to skip 3. We're going to do 4 and 5. Okay, so I'm going to save 3 for tomorrow because I haven't gone over that type of similar triangle problem yet. Okay, so I'll save that for tomorrow. But if you're done with 2, go to 4 and 5. We'll try those next. Now, technically, you may be getting a plus or minus 3 if you took the square root, but why do we not use -3?
Because you can't have.
Yeah, we're talking about the length of a side, so we're restricted to just positive values there. Now we can move on to our dVdt formula and then try to find the other missing piece that we need, which is dx dt. Now we have everything that we need. Find the SDT, right? X is 3, dx dt is -10^27. Now we can finally find what we're looking for, dx dt. So just a matter of entering all this into your calculator. Let's talk about units of measure here. Surface area, what's the unit of measure there? Meter squared over hour, square meters per hour. You feel good about this problem? Let's go to page 4, number 4, top the page, another cone problem for us to try. Okay, so anybody still need to look at this problem, number 2? Okay, go ahead and draw your diagram. Tank of water in the shape of a cone. It's leaking water at a constant rate of 2 cubic feet per hour. The base radius of the tank is 5 feet, and the height of the tank is 14 feet. There's water inside that tank. So we have a cone within the cone, basically. The water inside the tank is going to be taking on the shape of the container that it's in. So we're just going to look at a cross section of it because we need to build similar triangles in order to get that relationship between radius and height, because we have too many variables in the volume equation, and we need to get it down to a simpler equation formula. R and H represents the radius and the height of the cone, of the smaller cone formed by the water level. We know that water level is constantly changing, so we want to leave that R and H as variables to indicate that it's changing over time. But the container is staying consistent with as radius 5 and height 14. Similar triangles. We say the radius of the small cone is the radius of the large cone, as the height of the small cone is to the height of the large cone. The volume formula that we're working with is pi over 3 r squared h. We know we're going to have to find a replacement for one of these variables. I'm going to just cross multiply here. And let's go back to the problem and gather some more information. A tank of water in the shape of a cone is leaking water at a constant rate of 2 cubic feet per hour. The hint there is cubic feet. That's volume. Hour is time. This must be talking about ddt. Water is leaking out, so a negative rate. At what rate is the depth of the water changing? So we're looking for the rate of change of the height of water, the depth of water. So dH dt is the unknown. And the depth of water is 6 feet. Put a star next to the 6, right? Knowing that we're not going to touch that value until the end, even though there's all these places that it feels like we can insert 6 in for H, but we're just not ready for it. Now, this is a big hint. We're looking for dH dt, so it's just, we know that this is related to the H. So things will just go a lot smoother if I can just get my volume equation in terms of just H. So I'm going to solve for R and replace R with H so that I can get this to be a nice, clean height formula rewritten for this volume. And then I can find the derivative and I can get that all these variables to appear, and then I can plug in and solve. Okay, so continue with the steps and I'll show each step the way once you guys had a chance to try it. Want to find a way to remove R. So a way to do that is I can use my equation proportion that I built from similar triangles. If I solve for R, I'm then able to find a replacement for R. And my replacement for R is clearly in terms of H, which is what I want. So R gets replaced with 5H over 14. Once I made that substitution, we know we're going to do quite a few things before we can even get to the point where we're ready for the derivative. Okay, so make sure that you're taking the time to actively clean this up, because you're not going to be ready for a derivative. I mean, you could, but it's not worth the effort trying to go through product and chain rule when you can just do some cleanup and get to just relying on power rule. Okay, so we're gonna square everything inside the parentheses, so the 5 gets squared, the h gets squared, the 14 gets squared. We get 25 h squared over 196. Let's merge that with the pi over 3. So I'm gonna put the 25, the pi, the 3, and 196 all together as a fraction. The h squared and h can combine into h cubed. Now, you may have written it like this, which is fine, but my preference is push all of that in front, and have the h cubed outside. So it just feels like a number in front of my h rather than the h stuck within a messy fraction. That way, when you find the derivative, you can just clearly see all the separate parts that you're gonna need as you find all your derivative rules. Okay, so I put a box around that because if you get to that point, then everything is a lot easier, a lot more predictable after this. But up to this point, everything is kind of new, right? But you know, the funny thing is that it's not even the calculus that's the hard part. It's all the algebraic mess that we have to kind of get through to get to this point. Okay, so now that we have a nice clean volume equation, we can find the derivative. So v becomes dv dt. What happens to that 25 pi over 588?
It's moved over to the left.
Yep, it stays, right? It's just a coefficient that just hangs out in front. H cubed is what we want to find the derivative for. H cubed becomes
3h squared
h squared.
over dt.
And then every variable gets impacted by time. So we need to attach a dh over dt. Okay, so once we have our derivative all spelled out, we can look back at the problem and see what information we can start inserting in, right? So dv dt, we have -2. H, we have 6. So now is the right time to use the 6, okay? Anytime before this is too early. Okay, if you start using 6 anytime before this part of the problem, you're going to lose that ability to find your derivative correctly. So you want to leave this number, as tempting as it is, you want to use it at the beginning. You really want to save until the end. So now is the time to use it. We can insert 6 into the H. And then just make the calculator do some of the work for you. Okay, so 25 times 3 times 6 squared, that's 2,700. I'm leaving the pi out of my calculator, just putting it to the numerator to the side. And then now I have just a fraction that I have to move over to the other side. So if I want to divide a fraction to the other side, that's the same thing as multiplying that reciprocal to the other side. Good. So my 588 is going to come up to the numerator. My 2,700 pi is going to be in the denominator. So pay attention. That pi is now in the denominator. It's not just a notation, it's actually a value. So we can't just let that pi, be in the problem and expect it to be correct, right? That pi is a number. And if you put it in the denominator, it's different than if you put it in the numerator. So this is where it belongs. It belongs in the denominator. So in our answer, that pi is going to stay in the denominator. Okay, use your calculator to continue to reduce. I got it all the way down to -98 over 225 pi. Units of measure. We're talking about height and time. Height is a one-dimensional unit, so just feet. Time is in terms of hour, so feet per hour. Okay, part B. Part B says, at what rate is the radius of the top of the water in the tank changing when the depth of water is 6 feet? So at what rate is the radius of the top of the water changing? What is that referring to?
R, well, dr over dt.
Good, dr over dt. Okay, so we're looking for dr over dt. That's our goal. Now, if you think about this process, and one way that we can do this, we're not gonna do it this way because we have a much faster way. One way we can do this is we can go back to the volume equation and say, okay, well, if I want to find dr dt, then I'm just going to get everything in terms of r, right? So I'll solve for h, replace h in terms of r, find the derivative, dr dt shows up. I need to find radius to plug in, and then I go through all this process and I find dr dt. Okay, so that's one way to do it. But we have a bit of a shortcut because we have dh dt, and dh dt can actually help us find this a lot easier. And this is the shortcut. The shortcut is this ratio that we have in front of us at the very beginning that we gathered. R over 5 equals h over 14. Cross multiply, we get 14r equals 5h. Any idea how this can help us move towards our answer faster?
14 dr over dt is 5 dh over dt.
Right, we have this equation, right? So we can find the derivative of any equation as long as time is involved. Now we can jump directly to an equation that relates dr dt and dh dt. We have dh dt already. We insert that in, we can find dr dt. So that's a nice quick way to kind of jump between the two rates. Let's say you went through this problem thinking that you were trying to find dh dt, and then you realized at the end, oh wait, the question is asking about dr dt. I don't have to start from scratch. I can just use this to help me get to my derivative, and then plug in and solve for dr dt. Okay, so let me show you the steps. Okay, so we're looking for dr dt. We have that ratio that we have that we built, 14r equals 5h. It's an equation that we can use to find our derivative still. So 14r becomes 14 dr dt, right? R goes to 1, but we are asking for r's derivative, so it turns into dr dt. 5h, 5 stays, h becomes 1 dh dt. And now we can import that result that we got from part A, right? We have dh dt, insert that in for dh dt. And now we should have to solve for dr dt, which we can quickly find by just dividing. Okay, so insert negative 98 over 225 pi for dh dt. I want to divide by 14, but just to make it cleaner, I'm going to multiply by the reciprocal of 14 to move to the other side. So times 1 over 14. So numerators go together, denominators go together. Make the calculator reduce for me. Again, pi is in the denominator. It's going to have to stay in the denominator for your final answer. Units, radius is also one-dimensional unit. Radius is in terms of feet. Time is in terms of hour. So still feet per hour. Any questions? Okay, we're going to try number 5 next. I want to leave this up here for another minute for anyone who needs to look at this. But number 5 is a Pythagorean theorem problem. See if you can read the problem and draw your triangle out based off of the description. Okay, so give that a try. I will go through each step with you. All right, does anybody still need this on the board? Okay, so there's my right triangle. I have jet A traveling from San Francisco towards St. Louis. Jet B is traveling north from New Orleans to St. Louis. Find the rate of change of the distance between the two jets. So I'll call this horizontal length X, the vertical length Y, hypotenuse Z. So there's my Pythagorean theorem. Derivative. Okay. Label each of your variables. Okay, before we fill any of this in, let's just talk about this diagram for a moment here. So we have jet A and jet B. They're both headed towards St. Louis. We see the right triangle here, right? Here's the horizontal, here's the vertical, here's the hypotenuse. What's happening to X, that distance? What's happening to X as jet A gets closer towards St. Louis? Decreases, which means that the rate is also decreasing, right? The rate is decreasing, okay? Even though it's moving to the right, we don't want to associate right with positive. You want to look at that length, right? Imagine this problem in motion. If you can imagine that value growing smaller, you want that rate to be negative. If you can imagine that value getting larger, you want that rate to be positive. Okay, so jet B is traveling north, but what's happening to this length? Also decreasing, right? Jet B is getting closer. We know this distance is not going to stay as long as it is once it gets closer. All right, what about the distance between jet A and jet B? Also decreasing, right? So we expect all these rates to be negative because of the fact that these distances are closing in. Okay, so jet A travels due east to San Francisco towards St. Louis at 500 miles per hour. Therefore, how can we use that?
It's dx over dt.
Good, negative 500. So let me talk about what that means. Jet A and jet B is this distance between them is decreasing at a rate of 500 miles per hour. Each hour passes, the distance between them is going to grow smaller, shorter by 500 miles. dy dt, negative 600. The distance between jet B and St. Louis is decreasing at a rate of 600 miles per hour. Find the rate of change of the distance between the two jets. What are we looking for? dz dt. Ultimately, at the end, we're also expecting a negative value, right? So when everything's said and done, if we plug everything in, we should get a negative number in return. Okay, find the rate of change between the two jets when they are 300 miles apart. Z, yeah. And the jet is 100 miles from St. Louis. X, yeah. So how can I find this y at that moment of time? Pythagorean theorem, a squared plus b squared equals c squared. You'll get a decimal value. So you're just going to round it to 3 decimal places. And once you're there, then everything is easy. You can just plug everything in and solve for your missing dc dt and make the calculator do all the work for you. Okay, so try that. If you're done with this problem, I want you to start on page 5. And we'll at least get started with the homework. Okay, so page 5. Another cone problem. So hopefully we've seen enough cone problems where you feel like you're getting a hang of it and you're kind of knowing what to expect in terms of the next step.
Are cone problems and trough problems basically the same, except it's slightly different formula?
Yeah, I won't give you the trough problem. I'll just stick with the cone.
Probably those are step counts.
Hmm?
For the quiz, which are step counts.
Right.
Cones and other.
Right, cones and other shapes, but in terms of related rates, or in terms of similar triangles, it'll just be cones. So if you're good with number 5, go to page 5 and start trying number 1. And your homework is going to be page 5 and 6, 1 through 4. So we'll have you guys start on the homework because we have some time. Go ahead. Right, number 1 on page 5, cone tank, vertex down. Full of water, 10 feet across, 12 feet deep. So just be careful. Sometimes the problem gives you that the tank has a diameter of 10. Sometimes they tell you the radius, so just gotta make the adjustment accordingly. If they give you the diameter, then when you draw your similar triangle, you're gonna have to adjust to the radius. But if they give you the radius, then you just keep that radius. Water is flowing out of the tank at a rate of 12 cubic feet per minute. Find the rate at which the water level is dropping. The radius is 4 feet. So we're looking for DHDT. They're giving us R, and so I think that may kind of confuse us because we're like, well, before we would see consistency, but here I'm asked for DHDT, but they give me R. So what do I do with my equation? Should I get my equation in terms of H, or should I get my equation in terms of R? So I would target what we're looking for, right? Whatever you're looking for, let that kind of be your guiding in terms of what variable to target, right? Because your H will produce DHDT a lot faster than the R producing DHDT. So this is going to kind of indicate that even though you're given R, you're looking for DHDT, so you're going to target your H being your volume equation, just like how we've done in the past. Okay. But this R is a bit of a problem because we don't want R, we want H. So how can we get to H if I only have R?
Similar triangles.
Similar triangles. I don't think I talked about this with the previous problem. The previous problem, if we were to do this problem again, and if I did not give you height, but if I gave you the radius, we can still get to the height simply by relying on this equation, right? So if I have R, I can simply rely on this equation to solve for H. I'll send you guys the key tonight, but you guys will continue working through these 4 problems, and we'll go over these 4 in detail tomorrow as well. Okay, come and get your phones.
Students can write bus 4725 will write bus 4515. Students to write bus 4254 will write bus 468. Thank you so much. Have a good day.